If you know what you're looking for, most of these are going to be 2 steps, especially when you just start the unit. Like, let's look at this one. They've also given us a diagram. So we're doing question 9. The diagram is on the right. So there's a lot of words there, but the only word that's important is the last sentence. How high is the cliff, right? That's the only thing that's kind of important. Everything else is already given on the diagram, so we shouldn't be focusing too much. So what's our approach here? How do we find the height of that hill or whatever it is? Cliff. So this is your triangle. This is your angle of reference. This one right here, 70 degrees. Relative to this angle, which side is the height? Opposite, adjacent, or hypotenuse?
It's the opposite.
It's the opposite. So you're looking for the opposite. And which side of the triangle are you given?
The adjacent.
And you're given the adjacent, which is 50. And the angle is 70 degrees. Now the question is, how do you get O from this information? If you have 2, I need 2 of these, you have the third. You need at least 2. So we have the angle and the adjacent. We can definitely get the opposite. Is it sine, cosine, or tan? Which one uses O and A?
Tan.
Tan, and you're done. That's just tan 70 is equals to the opposite, which is the height, divided by the adjacent. So therefore, the opposite side is going to be 50 times tan 70, and you just plug that in. It's not going to be a whole number, but it shouldn't really matter. So the answer is 138 meters, and you're done. That's all. That is all. Let's look at 10. What's going to be our approach for 10? Do we find I or J first? Or does it matter?
J.
So that 8 is, let's see if it's actually 8. Anyways, it's scaled up. It shouldn't matter. What we need for this, we're going to do it a different way, but I'm just trying to see whether that 8 is the midpoint or not. This is not a good approach because this is not to scale, but anyways, the question is this 4?
Yes.
I think so as well. But it doesn't say it's the midpoint or anything. So you have an isosceles triangle. Does it cut it in half? Let's see if I can draw one. Does it always cut it in half? I think it does. But if you're not sure, here's another way of doing this, which is gonna make things a little bit more difficult, but it is what it is. This angle is gonna be 90, right? This angle is gonna be 60. I think it is 4, but we're gonna do this a different way. Let me just show you how you can approach this. I'm gonna say this is X. So what is the length of this? In terms of X in 8. 8 is the entire
8
thing.
minus X.
Yeah, it's 8 minus X. So now you have 2 different triangles. You want to attack the side length that they both have in common, right? So from the right, you have the opposite and the adjacent. It's going to be a tan problem. So tan 60 is going to be J divided by X. You agree? On the other side, tan 60 is going to be what? If you look at the left triangle, So tan is opposite over adjacent. So it'll be J over what? 8
8
minus
minus x.
right. Now you want to compare these two. Tan 60 is tan 60. J is J. Therefore, the x on the bottom must be 8 minus x. Do you agree? Just by their positions. Tan 60, tan 60, J, J. That means this ratio must be equal. Well, it is equal because that's tan 60. So 8 minus x is x. So therefore x is 4. So we've just proved that this is 4. Did that make sense?
Mhm.
So if you're unsure, right, just do what you can with it. But I think if you have an isosceles triangle, this is called the median line. It's going to cut it in half. So this is 4, this is 4. From here, it's super simple. Tan 60 is j over 4. So j is going to be 4 times tan 60. Plug that in a calculator. And for I, this is 60 because it's an isosceles triangle. Now you can't use, I guess you could use anything. But since we have this angle, we're looking for the hypotenuse of this triangle. I'm going to use sine. Sine 60 is going to be the opposite, which is j divided by the hypotenuse I, right? Therefore, I is going to be j divided by sine 60. And we know what j is from up here. We didn't plug that in, but we know what it is. So therefore, I is going to be 4 times tan 60 divided by sine 60. You plug that in, and that'll give you the answer for I and j. And you're done. That's it. SOH CAH TOA. Most of them are just going to be like 2-step problems. Like even this one. Do we use sine, cosine, or tan? We're looking for the length of the ladder for 11. Look at what you're given and look at what you're looking for, and then SOH CAH TOA, which one, only one of them is going to work.
Sine.
Sine is right. It's going to be sine 75 equals 2.8 over the hypotenuse, and then you just solve for that h in the denominator. This one looks like a difficult question. Alrighty, so we're looking for the diameter of the circle. I mean, if we have the radius, we can double that. What's our approach for this question? I'll give you a hint. You need to find the radius, which means you can either find this side or this side. What kind of a
What's
triangle?
28?
28 is the hypotenuse, because it's the only one that's not dotted, so I'm assuming it's the hypotenuse. What kind of a triangle are we looking at?
A right angle triangle.
Yeah, but it's one more level. It is a right angle triangle. Is it scalene, isosceles, equilateral?
Isosceles.
Isosceles, because both the side lengths of that triangle are its radii, yeah?
Mm-hmm.
So if this is R, this is also R. Now think about it. In an isosceles right angle triangle, this is 90. Since this side and this side is equal, this angle and this angle has to be equal, right?
Mm-hmm.
So if this is theta, this is theta. 90 plus 2 theta must be 180 because the angles in a triangle always add up to 180. So what's this angle up here? If you solve this, or you can also think about it intuitively. This angle and this angle must add up to 90, and they're exactly the same.
45.
45. So we know the angles. This is 45. This is 45. To find the diameter, you just need to find either of those side lengths. You can either find the opposite or the adjacent and double it. What do we use? Sine, cosine, or tan? We're given the hypotenuse.
You can use cosine or sine.
Exactly. So I'm going to use cosine relative to this. So cosine 45 is going to be equals to the adjacent, which is the radius, divided by the hypotenuse. So radius is 28 times cosine 45, right?
Mm-hmm.
Cosine 45 is actually, there's a number for this precisely. Cosine 45 is 1 over root 2. So that's the radius, 28 over root 2. We're looking for the diameter, you just double this. 2 times 28 times 1 over root 2. It is going to be 56 root 2. Cosine 45 is 1 over root 2 because of the special triangles. To find the exact value of cosine 45, you want to look at this special triangle. This is called the 45-45 special triangle. We'll do this later. I think we did this a while back. It's not really important for this problem, but if you want precise values, you want to use this triangle. If you plug cosine 45 into a calculator, it's going to give you an irrational answer, which is fine for this question, but some questions are going to ask you, what's the exact value? Anyways, this is the radius. To find the diameter, you just double it. This is what we get. What if we wanted to rationalize the denominator for this answer? We don't want a radical in the denominator. How do we go about rationalizing this? What will be the conjugate? Did we do this? I think we did it, right? When we were talking about
Mm-hmm.
the conjugate is going to be itself unless there's a plus minus thing in the middle. So root 2 is by itself, so the conjugate is simply itself, root 2. So on the numerator, you get 56 root 2, and in the denominator, root 2 times root 2 is root 4, which is a 2. So that'll be the exact answer. Or you can plug it in a calculator because it doesn't say find the exact answer, but later on it will. This will be the final answer for this question. Again, to recap, all we did was we identified it was an isosceles triangle. Because it's a right angle isosceles, these two angles must be 45. Using that, I found the radius cosine. Double the radius gives you the final answer for the diameter. Let's look at this again. They're gonna look difficult, but I don't know if they are. Oh, yeah, here we go. It says determine the exact value of x. All right, give me a ratio that's gonna give me x. Sine, cos, or tan. And only one of them is going to work. Actually, two of them are gonna work, I think. No, only one of them because we don't have the hypotenuse. What ratio is going to help us find x? Sine, cosine, or tan?
10.
Okay, so tan of what equals what over what?
10 of 30.
Is equals to 1 over x, right?
Mm-hmm.
What is tan 30? It is 1 over root 3. Because now this one, now it says exact value. So there exists another special triangle. This is the 30-60. For the last question, we used the 45-45. And for this one, it's 1, 1, root 2. For this one, it's 1, root 3, and 2. So these are the special triangles. Tan 30 is 1 over root 3. So 1 over root 3 is 1 over x. Then what is x? So if you get something like this, what you want to do is you want to cross multiply. If you get a over b over equals c over d, when you do cross multiplication, this is gonna go over here. You multiply root 3 with 1, and on the other side, you go over here. You multiply that x with 1. So x is going to be root 3. And that's the answer. So this is root 3. All right. Part B, it says determine the exact value of y using the Pythagoras theorem. Okay, we know the bottom part is root 3. How do we find y? It's gonna
B
be,
squared root 3.
it's gonna look like this, right? 1 squared plus a squared plus b squared equals c squared. So 1 plus, what's root 3 squared?
3.
3. Equals y squared. So y squared is 4. So therefore y is 2. Because y cannot be negative. Technically, it's plus minus 2 mathematically, but because we're talking about side lengths, cannot get a negative number. So y is 2. That's the answer of part B. Simple. Part C says, find the sine, cosine, and tan of both angles. What do you notice? All right, let's try it. Actually, I've already built this over here. If you notice, this is the special triangle. Sine 30 is going to be equals to opposite over hypotenuse. Cosine 30 is going to be the adjacent over the hypotenuse. Tan 30 is going to be the opposite over the adjacent. Similarly, what's cosine 60? Maybe I should write it down here. Cosine 60 from that triangle we have up there.
The square root of 3 over 2.
Cosine 60 would be, so the adjacent to 60 is what? 1 or root 3?
It's 1.
Yeah. So it's 1 over root 3. 1 over 2. Sine, what's sine 60?
That's root 3 over 2.
That's root 3 over 2. And tan of 60, again, it's going to be the opposite. So root 3 over 1, or just root 3. What do you notice here? Look at this. Try to find the pattern. That's the question for C. These we can come off, right? We're just reading SOH CAH TOA. But the bigger question is, what's the pattern here? You notice 1 over root 2, 1 over 2 and 1 over 2, they repeat. Root 3 over 2 and root 3 over 2, they repeat, right?
Mm-hmm.
These are called complementary angles. Complementary angles mean you subtract it from 90. So look at this. Let's say you have sine of 20, okay? Sine and cosine are related. Sine of 20 will be the exact same thing as the complement of 20, which is you do 90 minus 20, you do 70. These two numbers, the ratios, are going to be exactly the same. That's what we have here. 30 and 60, right? If you subtract either one from 90, you get the other thing. In other words, sine 30 is cosine 60, and cosine 30 is sine 60. If I asked you, what's sine 50 in terms of cosine? What's the complement of 50? You do 90 minus. You do 90 minus 50, you're going to get a 40. So sine 50 is cosine 40. Sine 1 would be cosine 89. Similarly, cosine 89 would be sine 1. These two are related, sine and cosine. What's sine of 70 in terms of cosine? Or what's the complement of 70? We just do 90 minus. It'll be 20. So what we notice is that sine and cosine are complementary. If you have one ratio, you can get the other one by doing 90 minus that angle. On the other hand, tan is sine over cosine. That's the other thing. How did you get 1 over root 3? What we did was we did sine divided by cosine at that angle. 1 over root 3 gave us this. Tan 60, how did we get root 3 over 1? Well, we got it from the triangle, but you could have gotten it also from the ratio. Tan is sine over cos. So those are the two main takeaways. One is that sine theta will be, let me just delete this. Sine theta, sine of any angle, is going to be cosine of 90 minus that angle. Vice versa also works. Cosine of theta is going to be sine of 90 minus that angle. That's how sine and cosine are related. And tan is going to be sine over cosine. So here are the two main takeaways from this problem. Cool?
Mm-hmm.
Did that make sense or no?
It did.
So what's sine of 89 in terms of cos? What is this number? You just subtract the main one from 90, you'll get it. Just follow this
So
formula.
it's 1.
It's 1, yeah, that's it. Sine of 60 is cosine of what?
It's 30.
30, and you're done. The idea of complementary angles. What do they want us to do here? Just gonna briefly talk about this. It's kind of fun, I guess. I don't know. Here's a question, very abstract question, STEM question. Why is it cold in the winter? That's our question. Why is it cold in the winter? This has something to do with longitude and latitude. More to do with latitude. If you look at our planet, maybe I should put it here. It's going to be tiny, but let me just make it big just for our purposes. The sun is far away. So you see how the sunlight hits the planet, right?
Mm-hmm.
At the equator, this is the equator. Equator is like the center of the planet. Canada is here. Terrible drawing, doesn't matter. North America this is North America. There's Africa here. Australia is down here. Equator kind of goes through Africa as well. This is Africa, Asia is here, Europe is here, right? This is called the equatorial line. The sun hits it exactly, like completely. Whereas the surface right here is right angle. What this means is that the equator takes up a lot of the sun's energy. Now, if you compare that with, let's say, the polar regions, right? Which is up there. These are like the North Pole, South Pole, Arctic, Antarctic. So let's hit it here. Notice how it's not perpendicular at all, right?
Mm-hmm.
In the middle, it hits it and then the energy is distributed evenly. But when it hits the polar region, it doesn't even hit it properly. It hits it parallel. That means most of the energy is lost. That's why it's cold up there. The question is, though, why is it cold here? We're not at the polar regions. Why is it cold here? Why does it get cold in the winter? Right now in the southern hemisphere, in Australia or something, right now they're having their summer season. What's going on? Here's the idea here. Let me show you what's actually going on. So you know how Earth rotates around the sun, yeah? That's a
Mm-hmm.
pretty common knowledge. And Earth also rotates about itself every day. It makes one full rotation every day in 24 hours. But what doesn't quite get talked about is this idea. It's not as simple as just our planet going around the sun like this. Our planet is actually on a tilt. So it's not like this. This is what I'm trying to say. It's not like this.
Mm-hmm.
How it actually is like this. Over here, if it's perpendicular, then it's going to look like this. But up there, it's going to look like this. Over here, it's going to look like this. Over down here, it's going to look like something like this. This is the northern hemisphere, yeah?
Mm-hmm.
This is the southern hemisphere. Let's zoom in on this. This is right now. We're looking at it maybe today's weather or something right now. Let me zoom in on that. The sunlight is coming this way. So this is our planet. Its tilt is this way. The tilt is 23.5 degrees. That's our planet's tilt. So the sun is over here. We are somewhere over here. Australia and stuff are somewhere down there. Notice what's actually going on. The sunlight hits this part more than it does this part, yeah? See that?
Mm-hmm.
Which means this part doesn't get as much energy. Heat is basically energy or like sunlight. This part doesn't get as much sunlight because it's tilted away from the sun. This is in January. That's why the northern hemisphere at this time experiences winter, whereas the southern hemisphere experiences it's supposed to be Feb, whatever, same thing. Southern hemisphere experiences summer. Now, if you zoom in on this part, that's going to be July, mid-July or something, summer month. Let's look at what's happening over here. Let's zoom in on that. So how do I draw this? Now this is our northern hemisphere. The sun is here. This is our southern hemisphere. Look at the difference. Over here, the sun was this way. Southern hemisphere got more sunlight, hence they had the summer. But now in July, the northern hemisphere gets more sunlight. The southern hemisphere doesn't get as much. Yeah, you see that?
Mm-hmm.
That's the reasoning behind seasons, winter and summer. Right now, in some places up north, I'm talking about these places, they don't see any sunlight. And maybe that's not the best place. I meant like over here. So this would be like northern parts of Canada or even further north like Greenland or something. or maybe the Arctic. Arctic would probably be the best. Remember, Arctic is on top North Pole, Antarctic is on down bottom South Pole. The penguins are here in the Antarctic, not in the Arctic. So some places up north, they don't get any sunlight. So they have, it's dark for like weeks to months. It's kind of interesting. And in the summer, it's the opposite. They don't get any nighttime because they're facing the sun all the time right here. So it's like daytime there for weeks or months. So that's why we experience winter. The sun is here. The angle at which the sun hits the planet this way, horizontally, these are called the latitude. Lat is for horizontally. Sunlight reflecting here. Longitude is this way, up to down. This way is longitude. And that's just what I wanted to say. In the equator right here, the angle, latitude angle is 0. And in the middle of the Atlantic Ocean somewhere, the longitude angle is 0. This is 30, this is 30. This is 60. Now if I keep drawing, this would be 60. So that's the idea behind latitude and longitude, and that's how we navigate the planet. Planes, ships, everything kind of follows this system. It needs to know where it is. And that's what came up here. That's what I was trying to say. So latitude is horizontal, longitude is up, down. And we can denote degrees in minutes and seconds. Well, like I'll show you in this question. The first one is 25 degrees, 16 minutes. It says write that as a decimal. Now, where's that minutes thing coming up? Because we usually measure the longitude, the vertical thing, up-down thing, using a clock. That's how we measure it. That's why there's like a minute and a second element on it. But it's not too difficult. Here, let's do a quick example. Or let's just do this example. 25 degrees, 16 minutes. It says write this as a decimal. Well, so it's going to be 25 point something degrees. Now the question is, what is this decimal value here? And it's very simple. This is in minutes. If there was a double apostrophe, it would be in seconds. How many minutes are there? How many minutes are there in an hour?
There's 60.
60. So this decimal value, you take this number, 16, you divide this by 60. That's 8 over 30, 4 over 15. Can't do it in my head. It's 0.2667. And there you go. That's the answer to part A. You take your decimal number, you divide that by 60. Or so you take your minute number, you divide that by 60, and that will give you your decimal value. B is the opposite. Now they're asking us to write this using degrees and minutes. So the answer is going to be 48 degrees and something minutes. So how do you find that minute value? You do the opposite. Over here, we divided it by 60. Over here, we need to multiply this by 60, just the decimal bit. So 0.30 times 60 minutes, that'll be 18 minutes. So the answer is 48 degrees and 18 minutes, and you're done. These are used to navigate precisely. We can go to seconds, we can go to milliseconds. That's how you navigate, or you know where your position is exactly. Cool? A little bit of a tangent, but yeah, something that'll help you maybe down the road. What is going on in this question? Just steal their diagram here. Actually, do we need to? Let's see. All right, let's see if we can figure this out. So she needs to drill a well to an oil deposit. Where does oil come from?
The ground.
But what exactly is it though? Yeah, it comes from the ground, but what was buried in there for us to get oil now? There's another name for oil. Starts with an F, double F, something bad for the environment.
Fossil fuel.
Fossil fuels. What does a fossil and fossil fuels represent?
Like the remains of.
Exactly. So it comes from like organic matter that's been down there for a very long time. Comes from dinosaurs, amongst other
Mm-hmm.
things. So this is the lake. This is the bottom of the lake. And let's say the oil is here. This is the oil deposit. And it says the deposit lies 2,300 meters below the bottom of the lake. So the distance from the bottom of the the lake bed, whatever, the floor, full of like sand and stuff, from there to this distance is 2,300 meters. Where this is the bottom of the lake, and this is your fuel deposit or your oil deposit, label it all. The lake itself is 150 meters deep. So this distance by itself is 150 meters. The well must be drilled at an angle from a site on land. The site is 1,000 meters away from a point directly above the deposit. So let's say this is the site. What's the distance between the site and the point directly above the deposit?
1,000 meters.
1,000 meters. So there we go. That's our drawing. At what angle to Earth's surface should Jackie drill the well? So this is the ground, okay? If you look at the oil deposit from the ground, we can't really look at it. I guess you can use sonar or something. No, you can't look at it. You can't physically look at it, but I mean you can get like a graph of using sonar or some other technology. It'll show you what's in there. So the question is, at what angle to the Earth's surface? This is the ground, okay? See this? This is the
Mm-hmm.
ground. The oil is somewhere down there. So we're looking for this angle. We're looking down. This angle relative to the horizon, the horizontal, is this called the angle of elevation or the angle of depression?
Depression.
Depression. So let's call this theta. So from here, it's easy. It's just a sine, cosine, tan. Is it sine, cosine, or tan? You can only use one.
It's tan.
It's tan. So tan theta is 23 plus 150. So 2450 divided by 1,000. How do we solve for theta here?
You multiply by 1,000.
No, because the angle is missing. You need to use something else. You need to get rid of the tan. You need to tan inverse. When the angle is missing, remember you do the inverse. Theta is going to be the tan inverse of 2450 over 1,000. So tan inverse of 2450 divided by 8,000. The angle is 68 degrees to the nearest degree. And you're done. Cool?
Mm-hmm.
That's it. And that's how you can use some basic trig to answer some complicated problems. There's a lot that goes into it. This is obviously very superficial, very simple model, but usually what happens in a project like this is the very, very first thing you want to do is you want to do like an environmental assessment to see if the project is even feasible. Drilling is the last thing you do. First thing you do is you obviously you found it. Now you want to see whether it's even mineable. What if like you destroy the lake while doing it? Then yeah. And then you gotta get a permit and then you gotta find funding and yada yada. The drilling is the very last thing you need to do. You need to submit a report to the government to get a permit. And this didn't used to happen back in the day, but I don't know if you heard about this. We have Canada is very rich in like minerals and ores and stuff. We have thousands of mines. You heard about the gold rush?
Mm-hmm.
Yeah, exactly. So we opened a bunch of mines basically everywhere, but none of them are very scientific. The worst part about that is that now most of them are closed down, right? But now things are different. When you submit a report, initial report to get a permit for a project like this, you also have to tell them how you're going to close it off. You need to close it as well, properly, environmentally friendly way. This is very important now. But back in the day, no one cared about this. Why are we talking about this? Is because a lot of the leftover mines, there's thousands of them. I can't even count how many there are in Canada. A lot of those leftover mines from the 1900s, now they've started leaking whatever minerals into the water or into the nearest forest. That's a big no-no, right?
Mm-hmm.
So now you can't let this happen. You have to tell them how you're going to close it off so it doesn't impact the environment. It's very strict now. I guess if you have money, then none of that matters, but you can always lobby your way into it. Let's look at this next question. How tall is a tree? What's our approach here? How tall is the tree? Again, it's not that difficult. It's not like the last one because they've already given us a diagram. It's just a SOH CAH TOA problem. And then you add or subtract the 1.6. So we're trying to find the height of the tree. We're trying to find the opposite relative to the 48, right?
Mm-hmm.
What's our approach?
You use
Sine,
tan.
cosine, or tan? Yeah, you're gonna use tan. So it'll be tan 48. That looks like a 5. Tan 48 equals to the opposite. I'm gonna call this distance x from here to here. The triangle, basically the opposite side of the triangle. So that's x divided by the adjacent, which is 7.2. So x will be 7.2 times tan 48, which is 8 meters. So is 8 meters the height of the tree?
You have to add 1.6.
Yeah, so it's 9.6 meters, and you're done. Easy peasy. I don't even want to look at this. So many words. Mm. Who invented the compass? Or which let's say continent. Let's narrow it down to a continent. From which continent did compass come from?
Was it China?
It was China, yeah. This was back in, let me think. I can tell you exactly where this was from. This is back in the 15th century, 1400 something. How is that important? How do I know that? It's because America didn't exist back then, right? Columbus, whatever,
Mm-hmm.
they didn't find, we did have natives, but yeah, it was not very technologically advanced America. Europeans were the ones that were powerful, but in the 1400s, they were going through the Dark Ages. So they had a lot of war. They were not sailing a whole lot. So the Chinese actually started to become one of the bigger players in the ocean. And they were the ones that invented the compass. They are the ones that also invented the rudder system that we see. You know, the rudder system, whatever. Like this thing that points out. You have something sticking out, right? On a ship or a
Mm-hmm.
boat, and then you move this, and then this will go this way, you'll turn this way. They also came up with that idea. Anyways, let's look at this question. Let's talk about something else before that. Compass, what does it measure? It shows you direction, but what is it actually measuring? It measures the planet's Earth's magnetic field. That's how it runs. Same idea as how do birds know where to go in the winter, right? The birds always go south to warmer places, but how do they know where south is? Through evolution, it's pre-programmed into their brains. They kind of have like this built-in compass. They know where it is. They're pretty smart creatures, but again, they can't distinguish glass, which is, I guess, eventually they might. I don't know. But yeah, there's a lot of like bird deaths due to glass, especially during migration season. Anyways, the question was, how does a compass work? And the answer is that it follows the Earth's magnetic field. This is the Arctic, right? We talked about this before. North Pole is the Arctic. South Pole down there, the Antarctic. These are the geographical North and South poles. Compass doesn't care about the Arctic or the Antarctic. There exists something else, and it's not at the Arctic or the Antarctic. It's somewhere here. This is called the magnetic North Pole. And so that magnetic South Pole is somewhere here. This is the magnetic South Pole. And this is what the compass measures, okay?
Mm-hmm.
The geographical North Pole and the magnetic North Pole, they are different. But I think this is cleverly built into the compass. Even though it's measuring this on the display, I think you just do a plus 30 degree or something, and it'll kind of take you over here. I don't know if this specific compass does this, but you can kind of turn the magnetic North Pole measurements on this into the geographical North Pole measurements. It's not terrible. It's just a shift. It's just a phase shift problem. Not too bad. Where does the magnetic field come from? Why does Earth have a magnetic field? That's a complex question. The answer is this. You know, we have the Earth, yeah?
Mm-hmm.
We have the crust. This is the thick bit that we are on. This is solid, usually made up of rocks and whatnot. Inside the crust, we have the mantle. This is what the crust lies on. This bit is the mantle. Inside the mantle, we have the core. The core is made up of two different things. It's made up of the inner core, and it's made up of the outer core. The inner core is the densest and the hottest part of the planet. Pure iron, like solid iron. I'm sure there's other metals in there as well, but iron was one of the first metals to form when the planet was forming billions of years ago, 4 billion years ago. So it was dense, it got sucked in to the very center. It's very warm. but this part is not important. What's important is this part, the outer core. So again, solid iron, this is solid. The outer core is not solid, turns out. The outer core is liquid. Again, it's very hot. It's like molten metal, iron and whatnot, but the outer core is liquid. The inner core is solid. So now what happens, because we know the planet is revolving 360 degrees every day, right? It like
Mm-hmm.
finishes one revolution. This thing and this thing, they're gonna be moving at different speeds. Water or liquid and solid, they don't travel at the same speed. Because of that speed difference, there's a disturbance, and that disturbance is what leads into the planet having like a very complex magnetic field. And the magnetic field, it's not always north to south or south to north for our planet. It reverses from time to time as well, and the reversal is completely random. We haven't figured it out. Maybe that someone will eventually figure it out what the idea behind that is, but it's very random. I think the idea behind this is from quantum physics. We'll see it eventually. And that's the idea behind magnetic fields. It's because of the difference in the core of the planet. Anyways, let's look at this question. How hard could this possibly be? So let's say this is their camp. They travel 240 meters before meeting their first orientation checkpoint. All right, so this is our first checkpoint. They turn, creating an angle of 42 with their previous path. They can only go this way. This angle is 42. And travel another 180 meters. So this is 180, this is 240 to get to the second checkpoint right here. And then they turn again and travel the shortest possible path. Shortest possible path. What's the angle? It's called displacement. Let's say you have A here. Let's say you have B here. There's an infinite number of paths you can take, but only one of them is the shortest. This straight line. This is called displacement. What do you think this angle is?
90.
90. Shortest possible path means you're looking perpendicular. It's going to be 90 degrees. So they will end up back there somewhere. And this is the shortest possible path. And there we go. That's our triangle. The question's asking us for the area. Again, how hard could it possibly be? The area is going to be the height times the base we don't know divided by 2. How do we find base? This side. Sine, cosine, or tan? Only one of them will work. You're looking for the, actually, no, multiple things can work. That's my bad. You can look at, you're given the adjacent and the hypotenuse, right? You're
So you
looking at
can
the,
use Pythagorean theorem.
yeah, we can use Pythagorean theorem. There's something wrong with this diagram. What's wrong with this diagram? 240 is not the longest side of this diagram. This should have looked like this. That's my bad. Shortest distance means perpendicular to your initial path, perpendicular to this path. So
Mm-hmm.
yeah, now it's better. Again, nothing changes, so we're still looking for this. We can use Pythagorean theorem, so it'll be 240 squared minus 180 squared. So that side length there is some number. Give me a nice number. Nope, 159. So you just do 240 times 159 divided by 2, and that's the end of the question. 19,080 meters squared. That's the area they would have traversed. Or that's the area of the woods, this part in the middle. And we are done. Did that make sense?
Mm-hmm.
Did the mumbo jumbo about the magnet thing make sense?
Yeah.
The magnets are cool. I like magnets. Um, you ever heard about what was the name of this? Go what the name is. Um, there's a train system. Hyperloop is the name. Have you ever heard about this?
I think I have.
Like this is like Elon Musk's project that he pitched once upon a time. So there's a train, okay? Not a very good drawer, but there's a train that would travel not on electricity, not on gas, not on any sort of fuel, but it would travel due to the pressure
Magnet?
difference between magnets. Yeah. Clean source of energy, super fast, probably faster than a bullet train as well. This is something that was being pitched, and I think they made a demo as well, which kind of worked, but we're too early, I think, for this. This is going to be another one of these new inventions within the next 20, 30 years, maybe. But look forward to this if it ever comes. I think it will, because I think it's a cool technology, and we're always looking at clean energy and innovations in transportation. All right, let's call it a day there.
Okay, thank you.
See ya.